Palo Alto Network's firewall, my IPv6 addressing concepts. I want to kind of start to take a look at a little bit of an introduction here just to familiarize yourself with the basics of IPv6 because it's becoming more and more popular. We'll see a lot of things start to come up as IPv4 really depletes in the world or becomes exhausted, I guess is probably the better way of looking at it. You have no more addresses. So we're going to start to see a lot more for IPv6. It was introduced originally in PAN-OS 4, very little anyway, a little bit more in version 5, but honestly now that we've gotten to 6, cross this out and just kind of mark it there, there's a lot more seriously functional stuff that we can do with IPv6. So if you're running into a dual stack environment, this is definitely the way to go with it, or I guess maybe if you're over in Europe you're only running a single stack but it's all v6 these days, or Asia for that matter. You know, there's a lot of other places globally that are running out of addresses faster than what North America is. Yeah, we're a little slow that way, but is what it is. Not going to get into that debate. Here, though, we want to be at least vaguely aware of what IPv6 means to us. So I'm going to take a little bit of a sideline for it and talk about what the addresses are, what formats that we might have to get used to, what things you might see, not just from an examination standpoint, but from a real-life standpoint, at least to be vaguely familiar with these types of things as we go along here. So let's kind of take a quick dive into the wonderful world of IPv6 and what it's going to mean to us along the way. So now that you got a little bit of flavor for this stuff, it's kind of good to give a quick little segue and highlight IPv6 as far as what we see in the Palo Alto world. Okay, so basically Palo Alto has IPv6 support. If you look at device and setup, and then session settings, okay, under here, one of the important things is going to be to check the box that says Enable IPv6 Firewalling. All right, so you'll definitely want to do that. Put a check mark right there. Now, once that's done, we have really a lot of things as far as what we're going to be supporting in there. Okay, so we do have IPv6 addressing. You know, kind of like we talked about here. We have it in general, so my layer 3 interfaces and certainly in my policies. I do have static routes. I do have my dynamic routing, well, at least on OSPF v3, and we talked about that in our layer 3 nugget in here. I do have ICMP v6 support specifically for my neighbor discovery. Okay, so the ND stuff. I also will have some options. So, you know, DHCP we had before, but I have DHCP v6 or my auto configuration, what we call Slack. So some of those options in there, there's really not support. So no IPsec or SSL VPN. Okay, so there is no support for that at this point in time. Not saying that it won't change, but you know, 6.0 anyway, or 6.1 does not have support for that. Typically, IPsec is actually built into IPv6 as far as a host-to-host protocol. So, you know, from a policy point of view, we can permit it, but there's not anything as far as the decoding or the termination point at this point in time. All other forms of networking, traffic classification, and threat prevention are supported by are supported with IPv6 in PAN-OS 6.0 and later. I really want to go ahead and get started with the addressing and subnetting. Now, I mean, you know, honestly, subnetting from a conceptual standpoint works the same in IPv6 as it does for everybody else. But one of the things that we kind of have to remember is that we're going to have a whole lot of addresses here. Specifically, now instead of, 32 bits is what we had in IPv4, right? So now we have 128 bits. So 2 to the 128th is an awful damn big number. Specifically, well, let's kind of take a look at that. So I do actually have that on here. So 2 to the 128th power is a big number. So when we start looking at this, when we get into, and get rid of those little bracket thingies, All right, there we go. So when we get into this, when we start looking at the details for stuff in here, this is 340 undecillion, just in case you cared. Okay, so 100,000, let's see, 100,000, million, billion, trillion, quadrillion, quintillion, septillion, sextillion, octillion, novillion, decillion, undecillion. Vast collection of useless knowledge. It's also represented as roughly 10 to the 38th power. So, you know, however you want to look at it, but it's a whole lot of zeros in there or a whole lot of numbers. So an equivalent factor for things. Okay, so just doing some basic, math stuff. So 2 to the 128th equals 2 to the 32nd times 2 to the 96th power. So this, of course, is IPv4 space. This, of course, is a whole lot bigger. Okay? That number right there is about 79 octillion. So little small things. I do have the number breakouts. I can actually show those on here for you if you're interested in that. So 2 to the 96th power is roughly 79 octillion addresses. Now, out of that, though, you know, there's a whole lot of things that are going on. And I'm just going to do the number overviews really quick just to impress the crap out of you guys. Warning, don't use this as pickup lines in a bar because it really doesn't work very well. I've tried. So, our networking space, once we start looking at our 128 bits, the general rule for things is we're going to be splitting them in half. The base RFC tells us that we're going to have 64 bits for a network address, and that'll become very important in just a little bit. But even at 2 to the 64th power, that is another large number. So what, 100,000, million, billion, trillion, quadrillion, quintillion. So 18 quintillion addresses per network. From a design point of view, I would highly advise not putting that many hosts on there. But that's kind of beside the point. You know, even when we start looking at that, you know, so that's both the number of networks and the number of hosts per network, since we slice it right down the middle. Even looking at that, that means that we're going to get roughly 2.5 billion networks per person on the Earth, and still won't really run out of space. How's that for a whole bunch of addresses? We're definitely not going to have the class full problem that we did with IPv4. Okay, that part we don't have to worry about in there. But, you know, you still get the idea. There's going to be lots and lots of bits to play with and lots of things going on for how we're going to mark stuff up and how we're going to do them. The nice thing, well, I shouldn't say the nice thing, the confusing thing perhaps, or I guess something to make our life a little bit easier for it, these numbers are not going to be dotted decimal. So at least we don't have to count that high for things. What we're going to have is a total of 32 hex characters. Okay, so our 32 hex numbers or hex characters that you'll have, you know, because of course we can spell things now, which is pretty cool, are going to be broken up into 8 chunks. Now we'll have a number and then a colon, then 4 more, colon. So you kind of get the idea for how this is all going to lay out. So that's what, 5, 6, 7, and 8. All right. So that's going to be an IPv6 address. It's going to be about that long, that many characters anyway. So 32 characters long with colons in the middle. Now, each hex character is 4 bits. So each of these is going to be 16 bits long. Going to give you that idea. 16 times 8, 128. All cool with the math. 4 bits is called a nibble. So we get in the binary, our octet is 8 bits, which is also called a byte. So 2 octets, or our chunk right here, is 16 bits. 2 bytes, I call it a mouthful. Again, not exactly a technical term. The industry hasn't quite caught up with me on that, but just for point of reference right here, always good to know what it is we're talking about. So 2 bytes is a mouthful. Don't want to make sure that you're hungry for IPv6. So all of that fun stuff, we're going to go with it. Now, leading down our addressing, though, there's going to be some changes to how we start to think about things, okay? So let's go ahead and take a look at the basis of our address as we go ahead and get in here. So let me go ahead and clear this stuff off. All right. So as an example, we have an address here. And again, told you it was going to be big, long, and kind of ugly, and that we could actually spell things. So there's going to be our Bad Beef Cafe in here. And we'll get all sorts of creative things. Believe me, we've seen this before. So those of you who are a little bit older and remember Novell NetWare and particularly IPX for a protocol, this is exactly the same stuff that we used to do back then. And, by the way, a lot of similarities that you will find between IPv6 and IPX. Mostly because in 1995, when IPv6 was first being created, that's when all the IPX guys were pretty much getting out of a job. So, yeah, you know, this is what happens with engineers. They recycle themselves and find new and exciting ways to get even. So, our big long address in here, and we're going to find ways to simplify it. Well, at least a little bit. If you have used, well, Unix systems in particular, you've probably seen this with MAC addresses for a long time. They have, 2 numbers and a colon between them, and we'll do things like remove all the leading zeros. So this 0 out of bad, this 0 out of the 200, these will all become 0 in here. Those 2 zeros will disappear, those 3 zeros will disappear. So we'll kind of get an idea for how we're going to lay things out to make our address a little bit shorter. Now, we can do one more thing, and that's any big chunk of zeros, so like this entire group right here, we can actually concatenate further with a double colon. Now, this isn't really a great example because there's only one set of zeros, but the bottom line is wherever we see the double colon in here, we're going to make sure that we know that only, click on that, I don't know why those things are in there. There we go. Get rid of those. Okay. So when we see this, we know that anything that's missing is going to be a 0. We are only allowed to have the double colon once, because like if I had it over here and over here, I'd have no idea how many zeros went on which side. So this just tells me that any missing numbers, really in this case it's just one set, but just in case it was more than one, we could still concatenate down to that. Now this has become really cool when it comes to routing, because right here, that's my default route in IPv6. That's about the only thing in IPv6 that is nice and small and easy to write out. Okay? So one of those things as we go. But this kind of gives you the idea of an address. So let's kind of take a look at some of those and see the, I guess conceptually, what we're going to come up with before we get into some actual live routers. All right. So from a familiarity point of view, we need to be aware of these different types of addresses, because we're going to see them on pretty much every interface that we have. Link local, as an example, always starts with FE80. And we'll get into the format of each of them in just a little bit here. My loopback is, kind of like the same thing as 127.0.0.1 is ::1 /128. So that is my single loopback address that everybody will have at that point. Site local, well, this is deprecated. I would still be familiar with it from an exam standpoint. This is going to be, was my first stab at private addresses. FEC0 /10. Unique local is the new way of doing things. So FC00 /7. And we'll get into the details on that as well. This is private addressing. Or both of these were, but this one no longer exists. Global addressing right now. Now really any address will work, but 2000::/3, which is from 2000 to 3FFF, in case you're feeling like doing the binary math. But those are my currently, I wouldn't say allocated because it's not really true, but my currently used space as far as giving to the various registries. So we have RIRs, or regional internet registries, like ARIN, like APNIC, like RIPE, that hand out public addresses to people. They'll do the same thing for IPv6 that they do for IPv4. This is the current range that we happen to be utilizing right now. Anycast Okay, so now Anycast is an interesting concept. So just kind of backing up a little bit, from a type of address standpoint, you have unicast, you have multicast, we all know and love from the world of IPv4, broadcast, and we have Anycast. These exist, by the way, in v4 or v6. Okay. So conceptually, a unicast address goes to one single device. A multicast address goes to a group of devices, okay, whoever happens to belong to that group. Broadcast goes to everybody, although in IPv6 there is no concept of broadcast. Okay, fair enough. We also have Anycast, which goes to the nearest of whatever it happens to be. Okay, so it's kind of like, oh, what's a good example for it? Well, DNS. Okay, my global DNS servers. When you look at your DNS, if you run a DNS server, you'll see that there are root servers, so root A, root B, root C, root D, so on and so forth. There's a number of them. It's not like root A is one giant server with a whole bunch of connections. Root A technically exists multiple places on the internet with the same IP address, and you'll simply route to the nearest device that has that IP address. In IPv6, we have a set of reserved addresses that reference that it's an Anycast. Okay? Because in v6, there's more of a group concept for things than there is individuality. So Anycast is actually a type of address in v6, which is the top, I'll write this over here, the top 128 bits of any network. 128 addresses. Addresses per network. Okay, so just 7 bits of addressing, but whatever your top range happens to be, those are reserved for Anycast. And we'll get into configuration, all the other fun stuff. Multicast always begins with FF. So /8, and we'll talk about those things in there. Solicited node multicast is one example of this. So going back to my idea right here, when we talk about no broadcasts being around, well, v4 did this really cool thing on how to figure out what your layer 2 address was. What was it called? Oh yeah, that was called ARP. Well, guess what? We can't ARP in IPv6, so that ain't going to happen. So we have other methods of doing things for figuring out whether somebody has my, duplicate address detection or stuff like that, or how I'm going to find what the layer 2 address is of somebody who is out there on my network. We do this via a solicited node multicast. Okay? So you will belong to a multicast group based on your address, and we'll try to figure out then what your link level or your layer 2 address happens to be. And I show others as needed because we've got all sorts of other multicast types going on, like all nodes multicast, all routers multicast, things along those lines. There's lots and lots of group addressing going on in IPv6. So we need to be familiar with conceptually how they're going to be set up in there and how we actually happen to use them in there. That's all my idea of addressing and subnetting. Now, kind of backing up a step. Okay? When I start to look at things, and I'll go ahead and clear this part off, when I start to look at things from a subnetting point of view, it's not like I have to worry about things any differently than in IPv4. So let me do this a different way. Where is my address? Okay, so I have a main address up here. Cool. Now, when I start to go through, normally my line is right here. So that's going to be a /64. So I have my network bits over here, I have my subnet bits over here. From an allocation standpoint, the typical things, now, and again, best practices will change up here. Originally, IPv6 was laid out to be a hierarchical scheme, namely the /3 that we had was for global, my registries would get a /16, my ISPs would get a /32, my enterprises would get a /48, and networks would get a /64. And the concept was that, when we advertise things out, we'd have really nice aggregation going up my routing table. Sounds really cool. That was cool back in 1995. Okay? What's different now than was different in 1995 to today's network? Particularly, well, BGP, not really different because BGP's been around, but the fact that a lot of people multi-home. So multi-homing messes this up. So good thought, not really going to happen. Yeah, whatever. But we still have the idea in here. So where we start breaking things out. So my /16, where is it? 16 right here. This was my regional registries. /32 is what an ISP gets. /48 is what an enterprise gets. Okay, so RIR, ISP, enterprise. So let's think about it from that point of view. I don't care which area that we happen to break it into, but same idea is going to exist. So at my enterprise level, my company gets a /48, which means these bits right here are all N bits, or network bits. These bits are subnet bits. And then these bits right here are host bits. It's exactly the same concept as what I do in IPv4. I have my overall network that I'm given. I have whatever subnet, VLSM. I can draw the line wherever I feel like, but I'm drawing my line, and then I have my host bits on the other side of that. That's the concept of subnetting. So the good news is I don't have to do anything different. At a binary level, it's going to work exactly the same in IPv6 as it does in IPv4. So we don't have to learn anything new, other than I would say that it's more important to get down to the binary. Okay? Because, so let's say that I'm going to draw my line, and I'm going to subnet. So I have my enterprise as a /48, and I have 4 campuses that I want to split things in. Well, 4 is 2 bits. Okay? So what that means is I'm going to do a /50 per campus. Well, that draws the line midway through this hex character. Okay, so that's kind of my catch. Remember, a hex character is 4 bits. If I'm only using 2 of them, so /50, so /50 per campus, then I'm drawing my line right in the middle, right in there. So I need to learn binary, especially when it comes to my hex portion, and how to split this stuff up, just to be sure. If all I'm doing is operating on very simple boundaries, this is no big deal. That is addressing and subnetting for IPv6. So one last one I do want to kind of expound upon a little bit for my addressing and subnetting part is my unique local addressing. Okay. So like I said, it is the FC00:7 that's set up in there. There's really 2 different pieces to that. Okay. So the FC/8 is going to be globally assigned. That's really not working right now because nobody's running a database. I think it's lack of financial support kind of idea. No money, not going to happen. FD/8, however, is available and used. These are all spelled out in write this on here. So RFC 4193, just in case you feel like going and reading the algorithm or anything. But so the FD00 is actually in use right now. We can get to it. We can use it. This is the version of private addressing for IPv6. Remember, there is no NAT in v6. So that's going to be kind of a big thing. Yeah, okay, there's v6, v4, v4, v6. NAT between protocols. There's not v6 to v6 NAT per specification. Not going to be allowed. So since we can't do that, we won't run into the same problems that we have currently with private addressing. This is also why the site local addresses were deprecated, because they all used the FEC0 and had overlapping ranges and ran into problems for how we use our networks today. Remember, back in 1995, completely different world when they came up with these ideas. So today's stuff is going to be evolving as far as that goes. So we have this in here. We have the 8 bits that are assigned to us in the FD. Then I have a 40-bit unique identifier. What this does is it gives me a /48 to play with. Okay? Now, if I want to get into this, go ahead and clear that part off. If I want to get into it, the best thing that I would say is go out to 6s.net and go into their tools /grh/ULA. Let me kind of pop that up right over here. So we get out of here, and these guys are great for IPv6 resources. So as you're studying or playing, or if you want to tunnel in, from your network into V6, the V6 internet, the interwebs, okay, all those things, go ahead and do so. I absolutely recommend playing with it. If your provider gives you V6 directly, cool. But still, play around as much as you can. But anyway, 6S on here, go down to the tools section over on the side, and then where GR8, so my Ghost Router Hunter, I can see that right here. That's where we're going to have a lot of those tools, and particularly in here is where I'm looking for the ULA. Okay, there's different things that we'll find in here, but essentially this will use an algorithm based on your MAC address. Okay, so it is kind of playing around a little bit, but you'll get your information in there, and you'll be able to register it as well, so that somebody else won't pretend to take the same number. Again, this is not a globally assigned thing, so there's really not any teeth behind it, so kind of take it as you will, but the concept is to give you a set of private addresses that nobody else will be able to play with. Until we get to the point where the global registry is up and going, and is what it is. But the more we get into V6, the more we'll start to play with this, and the more we'll start to go down that path. So that's going to be ULA, and that really does wrap up my addressing and subnetting portion. So EUI64 is going to really give me my idea about where do I get my address from. Okay, so I mean, everything that we've looked at, well, so far anyway, as far as giving information from our addresses in here, I have my network side of things, and then I have my host side of things. Right. Network is going to be assigned to me. I may have to subnet it, but that's all perfectly cool. But the magic comes in the host. And it's how we're going to assign that and what we're going to do. And I mean, I have lots of options. We're going to go through some of those a little bit later, but you're going to get the basics of how we get that information from knowing what an EUI64 address happens to be. Now, this is going to be an extended unique identifier, is what EUI stands for, and it's 64 bits long. Okay, now that's kind of interesting in and of itself, because nothing else that we have available to us is 64 bits. Now, back in the old IPX days, and this is really ancient stuff, so I suppose we have our little stick man, and he's got a cane. Okay, so back in those days, though, I had a total of 80 bits that I was playing with. That was everything that was going to be involved. So I had, what did I have? I had 32 bits for a network ID, and then I had 48 bits, which was my MAC address, or host ID. And that was where I got all the information in there to get my IPX address. Like I said, we have all those people way back when who got involved from IPX in coming up with my IPv6 stuff, so that's where we're getting some of this information from. Now, 48 bits does not exactly directly translate into 64 bits. Or does it? Okay, now that's kind of the catchy part. So I'm going to get rid of my bad artwork here, and let's come up with, kind of a test. Okay, whoops, so see where we're going to start with. And really, I start with my MAC address. Now, out of my MAC address, okay, so this is just something, this happens to be the machine that I'm working on right now. I just pulled a MAC address from it. Now, out of that, there are two different parts. Okay, so this over here is known as the OUI code, which is Organizational Unique Identifier. These things were assigned by the IEEE to any manufacturer who happens to make network cards. And they're sequential order, which, if we're doing spanning tree stuff, that's kind of important for that. But otherwise, it's just a number. We don't care. But that number comes with our cards, and then what they do is they'll put the host portion on it based on how many cards they happen to make. So they have 24 bits worth of information, or roughly 16.7 million per OUI code that they have to get on there. So that's how we play with things. Now, okay, again, useless knowledge as far as where those things come from and how they're broken up, but that does become important because this is also how we're going to break things up in IPv6 for my EUI64. Is I will break everything in half, and what I'll do is I'll insert a code in here. So FFFE will go in there. And, same thing at that point, so I just can put colons. So E8 FE50, and over here 2917 and 68. Now, I'm not exactly done yet, okay? This would be a good place to start, but academics, okay? So in my first bit, or first byte over here, my most significant byte, so 6, let's see, what is this going to be? It's going to be 0, 1, 1, 0, and 8 is 1, 0, 0, 0. Okay, so this is what those two nibbles are in binary. And when I start looking at this, I have two important things. So that bit right there is known as the I/G bit. Okay? And not entirely useful for this part, but that bit tells me whether it's going to be a unicast or a group address. 0 being I for individual, 1 being G for group. Okay, yeah, and it kind of gets back to how we look at things from a multicast perspective or from a broadcast perspective. Anything that we're going to see in there, that bit would be a 1. Okay. The next bit, however, is where I'm going to go. And that, my second bit, is known as my U/L bit, which stands for universal or local. If it's a 0, it's a globally assigned address. If it's a 1, I have locally modified it. Now, and again, kind of one of those things where you go, really? But what we do is we actually flip this bit. So if it's a 0, I'll make it a 1. The other catchy thing is if it's already a 1, I make it a 0. So kind of watch that in your show commands. But that translates this right here into what would be, 6A, or 10. So I will modify that right there. So 6A 1729 FF FE E8 FE50 is going to be my EUI64 address. EUI64. Now, again, I kind of sigh about it because I look at this going, okay, I went from 48 bits to 64. Are you telling me you can't figure out that I changed something? But whatever. Is what it is. Some programmer wrote, read in the RFC, that's what it said do, so they wrote it in their code without thinking, and it just does that. Cool. Is what it is. We're going to have to live with that. But no, this is how I get my EUI64 format, which means that everybody who has a MAC address, which, is kind of everybody, can automatically figure out what their host address is on an IPv6 network. So this, again, was created way before what became popular? DHCP, which, by the way, we do have a DHCP v6, but again, these mechanisms were in place ahead of time. So this is where I'm going to get my default addressing or my EUI64 stuff. Now, even that being said, I can get in here and have other types of addressing. So what I have in here, so this is predictable and gives me my MAC address. Some people look at that and say, that's not very secure. I don't want people to know what my link local address is because those hackers and all the bad people and everything else don't want to have that happen. So I'm going to come up with privacy extensions. And originally, so this is actually a second one, so is RFC 3041 is where the privacy extensions came out to begin with, evolved into 4941. But this gave me a different way of hashing my address. So I can actually change my host local address every so often, whatever my policy happens to be. Different vendors do it different ways. Most vendors like Cisco and stuff like that don't do it, okay, because it's insane. But Microsoft, a bunch of Linux or Unix type variants, things like that, can do private type addressing. All right. So just kind of well, not really brief, but a good overview anyway to the introduction to IPv6 addressing, little subnetting in there too, just so we have an idea as to what we're doing, but particularly the addresses as far as our concerns for things that we may end up seeing, that ULA, the unique local address, and of course the wonderful world of EUI64. And really it doesn't matter whether I'm talking about a router or a layer 3 switch or a firewall in this case, my concepts for IPv6 are all going to be the same. So hopefully a good introduction didn't scare anybody off too much. You and I are having a good time going through all this. I know your brain's probably full by this point, but it's good stuff to be aware of and worthy of the review on there. So I hope this has been informative for you, and I'd like to thank you for viewing.